let me briefly introduce Professor William. Yes. We know him like Bill, okay? He is Martin Pomeranz Professor of Physics and Astronomy at the University of Delaware. And he's extremely famous in our community for his works in turbulence theory, plasma physics, fluid mechanics, statistical mechanics, with a particular application to solar wind and coronal phenomena. So let me say that he is a recipient of the James
McElwain
Award from the American Physical Society and the University of Delaware College of Arts and Sciences. He also got a scholarship award. He got the Ruth Gall Prize sponsored by Alage.
Alaje. It's Espanol.
Alaje. Spanish. So in 2018 and 2019, he got the James Clerk Maxwell Prize in Plasma Physics from the American Physical Society. He is also extremely famous in our community because he is the director of the Delaware NASA Space Grant Consortium and the Delaware NASA ABC Core Program. And
EPS Core.
Okay. And he is also co-investigator of most famous mission that we had on solar wind. So cluster, MMS, solar orbiter, Parker Solar Probe, and in the future, let me call the Helios worm, which is extremely important in our community, but also interstellar mapping and acceleration probe in Punch and so on. I would like also to mention that next week in EGU, you will have Lawrence lectures for this year, and so please go on. Thank you.
Well, thanks, Giuseppe.
Just another question for people that are connected. Please, the question will remove the question at the end of the talk, and you have to raise your hand in the Zoom. Thank you.
So I shouldn't have sent you so much material because you spoke for a long time. But I'll tell this group a secret. Don't tell anybody, okay? That this lecture that I'm giving today is my practice lecture for the Lorentz lecture. They're the same length, and I thought, why not give it twice? Then it'll be better when there are more people here. But this is a distinguished audience, and I'm very glad to be here. I was chatting with the local people about whether this is where I went in 1980 when I visited Vavassano and Maria Bice and Marino Dobrovolny. But I couldn't remember. And my understanding is it was kind of close to here, but not exactly here. So it's nice to be back anyway. And a few weeks ago, I was at Denise's place, which is also close by. Anyway, this was a kind of generic title, but the first part, okay, I'm going to look at nonlinear and statistical behavior, but the main theme of this talk is structure. And I'm not going to talk very much about the mathematics of structure. You can ask Giuseppe about that later. But I wanted to just give a general overview. And the point is to build up to the connection that I want to make at the end, suggesting there's a connection involving all structure at all scales. But we'll see if I get to that. So I want to start by telling you, well, you know about these things, that in lots of examples of turbulence in hydro and in MHD, in reduced dimensionality, plasma and hydro, and in various forms and in different parameter regimes, these things apply presumably to the solar corona, solar wind, interstellar medium, ionospheric plasma, which is actually like a kind of a two-dimensional guiding center plasma. At least it used to be thought that way. And one general common feature is the appearance of power law spectra in wave number, usually involving velocity field, magnetic field decomposed into mean and fluctuation, as well as density. But I'm not really going to talk about spectra very much. But I do want to remind you that these kind of spectra with slopes somewhere near the Kolmogorov value are sort of seen in a lot of places. Solar wind. This is a really, I have yet to see a better -5/3 than this one I did with Mel Goldstein in 1982. But you also have from the Armstrong et al. The great power law in the sky. This done with structure functions. This Harmon and Coles from scintillation data in the corona, and the famous Grant Stewart and Wallier power law in a tidal channel. And actually, there's a connection between this plot and the last slide I will show at the end, but I won't describe it right now. But remember Grant Stewart and Wallier, okay? Because this was, a lot of people thought that this was the first conclusive evidence of Kolmogorov's slope for the power spectrum. 1962, I believe. Anyway, just a couple of words about general properties of turbulence, most of which I'm not going to be talking about. But if you look at Fourier modes in turbulence, this is from a simulation, of course. In MHD, you do see evidence of wave activity. Certain Fourier modes kind of mainly rotate around in the complex plane at an angular frequency that's given by their frequency of, say, Alfvén waves. But the more energetic modes tend to just kind of random walk in the phase space of real and imaginary parts of the Fourier coefficients. And this is just an example of those two types of behavior. And if you look in the time domain, remember the spectra I just showed were inferred at least to be in the spatial domain, wave number. But this is a real frequency spectrum from a simulation. It's the so-called Eulerian spectrum. You put a probe in, you measure a long time series, and you look at the spectrum of that time series. And it also has kind of power law behavior at high frequencies. The natural frequency here, because the mean field is 8, the natural frequency is 8. And you can see that you have kind of a pretty big spike there and a few harmonics. But actually, the area under this curve is not dominated by the area under the solutions to the dispersion relation. Instead, it's dominated by decades worth of low frequency Fourier modes. And when I showed this plot a decade ago in Nice, Ariel Frisch objected to the fact that I called these zero modes, because for him, zero modes meant something much more sophisticated than what I'm talking about. But modes approaching zero frequency, these modes have periods that are almost 1,000 times longer than the dominant solution to the dispersion relation at frequency 8. So, and the reason I'm emphasizing this here is because the other plots were spatial domain, and this is the time domain, and that's where I want to come back to toward right near the end of the talk. So the main thing I'm going to talk about is structure in turbulence. I want to talk about structure in space, inverse cascade, for example, and also in time. That's something like what I was just showing. And I want to talk about small scale structure in space, like coherent structures, patchy correlations, regional correlations, which I think is I'm not saying that it's a really new subject, but it was new for us anyway. And finally, in time, small scale structure can give you extreme events. Now, in the end, I'm going to try to tie things together by actually quoting from the famous papers by Ubakov and Kolmogorov and trying to convince you of something. But that's really the point of the lecture. So, okay, turbulence, hydro, wind tunnel, Reynolds number about 15,000, flow around the suspended sphere. If you expose the picture for a long time, you see, well, a coherent structure, these von Karman vortices in the back of the sphere. If you take a faster exposure, you also see coherent structures, but they're much finer scale. So there's large scale and small scale coherent structures in this particular experiment. Solar wind, stereo data, expertly analyzed by Craig DeForest. This is Comet Encke, and he and I went through and labeled all the bright spots of the plasma blobs coming off the comet. And you see structure coming out of the corona. It's initially striated, and it isotropizes as you move out. You can actually see the Lagrangian tracks in this kind of experiment. It's interesting. We wrote a paper on this, and we showed that the statistics in velocity and real space are arguably consistent with some kind of Langevin equation, which is sort of interesting. So the structures are influencing the behavior of the plasma blobs. These are at multi-gigameter scales, by the way. You see structure or intermittency in all kinds of hydrodynamic experiments and simulations. Here's an experiment, a simulation of dynamics at cloud tops, and you can see the obvious structures. These are at many times the dissipation scale, so it's more mesoscale structure, maybe even large scale. Ocean, surface, air interaction, big structures. And of course, in the interstellar space, Porter et al. Did simulations of the mass distribution and the vorticity, actually. And you can see that there are voids and blobs of vorticity and so forth. So there's structure all over the place in every turbulent medium that you look at. And I like showing this simulation that Yan Yang did of a mixing layer in order to pull out some data to compare with Solar Orbiter, which we did in a paper by Kio Kiao, Ohm, if you know Ohm. Her name is unpronounceable. But this is a mixing layer, fast on the top, slow on the bottom, and MHD, and you see that it forms roll-ups and all kinds of structures of broad band. Since it's MHD, this is mostly large scale and mesoscale structure. But you can also do the same kind of thing, and this is the famous Karamabadi simulation. You can do the same thing at kinetic scales with a PIC code, and you see here the current density. And it does sort of the same thing that the MHD mixing layer does. In fact, if I didn't tell you that this was kinetic plasma physics down to electron scales, you'd probably think it was some kind of fluid model, MHD, but it's not. This is, I think, maybe 20 or 30 ion skim depths across. That's from the famous paper by Karamabadi et al. In 2013. And the thinnest sheets are at the electron inertial scales, more or less. So those are examples just showing you that you get structure at all scales in space. But let's talk about some paradigms for how you get some large-scale structure. I'm not saying that this is the explanation for all large-scale structure, but a lot of it, I think it is. So in my experience, the paradigm for generating large-scale structure is two-dimensional, incompressible hydrodynamics. And if you look at the system in a Galerkin approximation, in Vissit case, there are two isolating invariants, two ideal isolating invariants, and that's the entropy and energy. I think everybody knows this. Yeah, so it has these two invariants. Entropy means square velocity over 2, the energy per unit mass, and the entropy, the vorticity squared over 2, where the vorticity is the z component of the curl of V. But there's a lot of other systems that have more than one invariant. Two-dimensional guiding center plasma. I'm not going to go through all the details of these. Probably you're familiar with a lot of them. Three-dimensional MHD, energy, magnetic helicity, and causalicity in the absence of a mean field. 2D MHD, that you get rid of the magnetic helicity and you inherit the mean square Z component of the potential, or three-dimensional Hall MHD. And I think recently the Squire and those guys talked about three-dimensional MHD with FLR and finite Larmor radius invariance. There's a lot of these systems. And if you look at the behavior of these things in the ideal Galerkin limit means you expand in Fourier modes, you truncate at some point, you truncate the solution and the equations in the same way, and then you actually preserve these things pretty much exactly. You can, if you have a good code with small time steps, you can integrate for hundreds of thousands of nonlinear times and conserve everything, essentially up to round off. So that's a good thing to do. So if you have a system that has a finite number of degrees of freedom and and you have invariant quantities that survive arbitrary truncations of the number of Fourier modes that you have, then you can do a Gibbs ensemble. And this was originally described by T.D. Lee in 1952 and later exploited by Kreisman and Montgomery and Frisch and other people. So if you do that, if you do the Gibbs ensemble statistical mechanics with 2D hydro, you have two isolating invariants, and they're related to each other by a factor of k squared in the velocity Fourier space. You postulate a canonical ensemble. The equilibrium distribution is given by a constant times e to the minus, well, 1 inverse temperature times the energy, and another inverse temperature times the entropy, the mean square vorticity. And there's two inverse temperatures, alpha and beta, and you can easily show just by plugging these things in and doing the Gaussian integrations, you can see that the ensemble average of the velocity field spectrum is given by 1 over alpha plus beta k squared. And since you know what the mean energy is and the mean entropy is, you can write a little code to exactly solve for these temperatures. So this is exactly solvable statistical mechanics with no free parameters. And I have to tell a quick story that when I was a grad student and Dave Montgomery did this for 2D MHD, we went to Rutgers to Joel Leibowitz's Stat Mech conference, and Dave gave an evening talk. Dave, my thesis advisor, Dave Montgomery, with Mandelbrot sitting in the front row. And when Montgomery showed results like what I'm about to show, Mandelbrot said, Dave, how many free parameters, how many fitting parameters are in this theory? And Dave said, no, it's exact. There's no fitting parameters. The temperatures are fully determined by these constraints. And Mandelbrot jumped up and said, I didn't know there was any statistical mechanics for turbulence. And of course, I was in the audience. I thought, I'm kind of proud of the fact that Mandelbrot likes this stuff because it was my numerical work. So I was happy about that. But again, T.D. Lee started all this. There's no free parameters. It just requires a Galerkin approximation, which is pretty artificial, but it's pretty cool that you can do stat mech on one class of turbulence problems, right? And how well does it work? Well, Charlie Seiler, for his thesis in '75, did the Gibbs prediction for 2D hydro, and you put in arbitrary, almost arbitrary initial conditions. You time average the spectrum that you get. The solid line is the Gibbs prediction. The dots are time averages of what you see. Pretty good agreement. There wasn't really long simulations or really high resolution. Resolution doesn't matter so much here. In time, you can see that you get this condensation. These are the streamlines. You see that you produce large structures in the course of time. A couple other examples. Here's one that I did that's in Kreisman Montgomery, 1980. And in this one, we put 99% of the energy into this one mode here and low levels of noise elsewhere. And you run it for a few hundred nonlinear times and you get the X's, and there's the exact Gibbs prediction. So, now, by the way, Gibbs prediction, it predicts order 1 fluctuations at every point. And you see that you get scatter that are kind of order 1, but the general trend is definitely in agreement. It takes a very long time to build up the longest wavelength mode, which is one of the reasons why people who do this kind of work think about inverse cascade as taking long times, because the statistical mechanics relaxes most slowly at the longest wavelength for reasons that you can debate, non-local couplings or whatever, but it eventually does slowly approach the ensemble average. So you can do this in MHD as well. Let me show you a couple of the results from that. Here's the ensemble average predictions. I'm not going to go through all of that, but there's 3 temperatures now, energy, cross-helicity, and magnetic helicity inverse temperatures. You get exact spectral predictions. Again, you can back substitute the specified values of the 3 invariants. You can get the numbers for the inverse temperatures. If you do a particular run, this is one that my grad student Troy Stribling did in 1990. This is a particular run, time average for a long time. Again, much longer simulations than the earlier ones you saw. And here you see what the energy spectrum is compared to the Gibbs expectation, the cross-helicity spectrum, and the magnetic helicity spectrum. more and more condensation into the longest wavelength mode, that happens for all three of the invariants. This one I think is particularly interesting because it shows that if you can vary the magnetic helicity, everything else being kept constant, and if you look at the fraction of each quantity contained in the longest wavelength mode, that you see that as the helicity increases, you get a larger and larger fraction of, first of all, the magnetic helicity, the dashed, almost all of it, like 99% in the longest wavelength mode, if the magnetic helicity is like 0.7 relative to the energy. The cross helicity also condenses a little bit, not as strongly as the magnetic helicity does. And of course, the energy has to condense a little bit because to have magnetic helicity, you have to have some energy. So sort of the minimum amount of energy condenses to the longest wavelength, compatible with the magnetic helicity completely condensing to the longest wavelength mode. So this argument is what turbulence theorists, at least of that generation, Kreisman, Montgomery, Frisch, and these folks, what they consider to be the conclusive argument for the existence of an inverse cascade. More recently, people who, let me call them the Python generation, call inverse cascade anytime energy appears in the longest wavelength mode. In hydro turbulence, people call that backscatter. I mean, it's just filling up the phase space because it's empty. You have to have something there. But it's not a condensation. This is a Bose condensation, very similar to what people see in like superfluid helium and things like that. So condensed matter people would call this a Bose condensation. And we call it a condensation, but if you reinstate dissipation and maybe driving, then this tendency for the excitations to preferentially appear in the longest wavelength tells you something about the affinity of the longest wavelengths to attract excitation to those very long wavelength modes. So you can see how that would give you enhanced ability to populate the largest scales. And this is the way that we tend to predict the existence of an inverse cascade. So when you have a Bose condensation in the Gibbs ensemble, you would predict an inverse cascade. So in 2D hydro, you get energy inverse cascaded and entropy direct. 3D MHD, you get magnetic helicity inverse transferred and energy direct. Cross helicity is hybrid because it partially condenses. That's Troy Stribling's thesis. 3D Hall MHD, you have energies direct cascade, magnetic helicity inverse, and this hybrid helicity, which is the sum of the cross and velocity helicities, inverse cascades. 2D MHD, mean square magnetic potential, inverse cascades, energy is direct. And the 2D guiding center plasma has electric potential inverse cascading and mean square charge density direct cascading. And Charlie Seiler did that for his thesis. Now, so now we have our old standard picture of the Kolmogorov cascade, but if you have one of these situations occurring, and actually more than just these, but I'll come back to that in a minute, that if you have some tendency to condense, then you have the potential to have an active inverse transfer in spatial scales to produce long wavelength, let me call them coherent structures. Okay, the extra systems that can also do this are the ones that have quasi-invariance. What do I mean by quasi-invariances? Well, if you have some parameter varies that causes a two-dimensionalization of the system, then you can almost conserve, say, mean square potential or in a MHD system with a strong magnetic field. Or if you have strong rotation, you have the Taylor-Proudman theorem. It two-dimensionalizes, and again, you can almost conserve these special quantities, and therefore numerical experiments show that you actually get significant enhanced inverse transfer in these cases. I don't really want to call this a pure inverse cascade, so let's call it pseudo inverse cascade. It sort of has its inverse cascade with an asterisk, but it actually happens in numerical simulations. So here's our canonical case again, the two-dimensional Navier-Stokes turbulence. In this case with finite Reynolds number, 14,000, and this is the vorticity, and here's the vorticity initially, and we ran it up to 332 nonlinear times, and you see that the dynamics consists of the formation of these isolated vortices. They're not really isolated, they're sort of isolated, but they eventually, the big stronger ones eat up the weaker ones with these spirals. It gobbles up the vorticity, and the big ones eventually are there by themselves. There's still some dynamics, there's some ripples there, so it's really incorrect to call this an equilibrium. It's just approaching an equilibrium dynamically, and as a result of which, these very clear coherent structures appear at the longest wavelength. One of these pictures appeared on the cover of some book. Might have even a book by Gregory Eyink, I'm not sure. But somebody asked me if they could put it on the cover of a book. So anyway, if you have a system that behaves in these ways with this tendency to inverse transfer, you can also postulate the existence of a global relaxation process, which we've called, with Dave Montgomery, called selective decay hypothesis. You say that what should happen when you reinstate dissipation is that the direct cascaded quantity divided by the inverse cascaded quantity over time should evolve towards the minimum allowed value allowed by the geometric constraint. And Montgomery et al. Have many papers on this. But right away you can see there's a problem sort of, because for simple incompressible MHD, the pure selective decay hypothesis implies that the velocity goes to zero, which would then disallow alphanic fluctuations. So something is wrong. Whereas simple dynamic alignment, a la Dobrovolny, Mongenet, and Veltri, which I heard about for the first time somewhere near here, 45 years ago, that would require equal partition of velocity and magnetic field. They both can't happen. There's some kind of competition between pure selective decay and pure dynamic alignment. So what actually happens? Well, it turns out that if you look in the plane spanned by, for 3D MHD this is, spanned by the ratio of magnetic helicity to energy versus the normalized causalicity, quite twice the causalicity over the energy. If something purely selective decay, it would have to go to this point here at 0, 1, and if it was pure dynamic alignment, it would have to go to 1, 0. But what actually happens if you do a few hundred simulations is that they all move outwards. They don't all move outwards. Most of them move outward unless they're vorticity dominated. Then they're in this region 4 and they move towards the origin, which is very interesting. So this is a kind of crude classification scheme for most simulations of incompressible 3D MHD move towards these boundaries. But this boundary can be computed by minimizing the energy of b squared plus b squared minus Lagrange multiplier times the magnetic helicity minus another Lagrange multiplier times the magnetic helicity. And there's a solution to that. And the solution to that is a alphanic force-free Beltrami flow. The velocity is parallel to the magnetic field, so it's directionally aligned. The current is aligned with the magnetic field, that's force-free state, and the velocity is aligned with the vorticity, which is a so-called Beltrami state. The exception to this moving outwards, and you can compute this boundary, and I think Vincenzo Carbone was the first one who recognized that you could actually write this boundary as the sum of the squares of two of these quantities, and everything goes onto a circle, which Raffaella has written a lot of papers with the sphere, and the solar wind goes onto the sphere.
Invented by Roberto and Bruno.
Yeah, Roberto started doing
and
that.
Also Bruno.
And yeah, Bruno, yeah. Anyway, that sphere is actually you can derive that sphere from this minimization principle. Now, the shear-driven case is an exception to this because it goes to this region 4, which is sort of trivially, you still get this directional alignment, but it's kind of trivially, it's not really part of the surface, but it does occur in strongly shear-driven cases, probably switchbacks in the solar wind. Anyway, so there's this relaxation principle that gives you a way to predict these final states. Of course, the dynamic alignment all by itself, which again is conflicting with the selective decay, was originally offered by Anik and us and others as an explanation for why you get the alphanic states. But I think a better explanation is to include both types of processes if there is another process going on. And you can even look at the cross helicity in solar wind, and this is an interval identified by Len Berlage in Helios at 0.6 AU. You have this distribution of cross helicity values from inward to outward. And later, Voyager saw the same blob at 8 AU, and you can see that instead of being preferentially aligned to outward, the blob, if you believe it's the same blob, evolves towards zero cross helicity state. So it's not in region 1, 2, or 3. If this is relaxing, it's in the shear-driven mode. And there are large shears in the solar wind, so it's not unusual to suspect that. This is from Aaron Roberts' paper in '87. Well, this happens in systems other than the solar wind. It happens in a penning trap. We used to have a penning trap in our basement of the, not my home, but in the physics department. And I was actually the PI of an experiment for about 2 years, believe it or not. You shouldn't let me go near any experimental apparatus. But we ran it, and here's, this is the same thing as 2D hydro, but it's charge density and electric potential. And this is an image of the charge density, which is 1-to-1 with the well, charge density is the direct cascaded quantity. So it's like the entropy in 2D hydro. And here, this is at an earlier time, and you see that as in time goes on, these vortices, if you like, merge, charge density blobs merge, and look, they form a big coherent structure, just like you would expect from the 2D hydro picture. And we even generalized, this is from my student Rogers, who, by the way, is the gentleman who downloads all the data from Parker Solar Probe. This is Doug Rogers. That's the job he got. Good job. People get angry at him, though. We want more bandwidth. Give our instrument more bandwidth, but he does a good job. But there's actually a von Karman-like decay law that the experiments obey very well. That was in some papers in 2010, sorry. So global relaxation occurs in a lot of other systems, selective decay and solar physics examples. Here's some reverse field pinch data showing that you move towards a Taylor state. The Taylor relaxed state is a special case of this selective decay. And you can look at a generic 2D MHD simulation, and you can see what's happening. This progressive merger or reconnection between magnetic islands occurs through current sheets, and now reconnection comes into the picture as the way that they merge, just like in hydro, where bigger galaxies, so to speak, wrap the weaker ones around them and form bigger vortices. Here, reconnection acts to merge the magnetic islands and form bigger ones through magnetic reconnection, but this is not a talk about magnetic reconnection. Well, it could be. Well, okay, so selective decay and dynamic alignment are pretty good principles, but there's actually another line of reasoning that works in the phase space instead of the Fourier space. And going back to Onsager, he approximated 2D MHD as a system of line vortices, which is not exactly the same thing as a Galerkin approximation, but maybe notionally they have some relation. And he noted that they could have negative temperatures. Notice that those alpha and beta k-squared Gibbs things, one of them is usually negative when you form the condensation. So there's some precedent for that in the Onsager treatment of a line vortex gas. And Montgomery and Joyce in '71, in a very well-known paper, showed that if you compute the most probable state of a vortex gas, line vortex gas or line charge gas, you get this nonlinear Cinch-Poisson equation. And the solution to that can be shown to give rise to these big vortices. But those are for line vortices. How about continuum vortices? Well, 30 years ago, Dave and I did those simulations that I showed, where the vortices merge and form these big ones. But it turns out these big ones, these big vortices that form, aren't actually quite the selective decay vortices. If they were selective decay vortices, then the correlation between the stream function and the vorticity would monotonically increase, and it kind of does. You're moving towards selective decay. But if you correlate it with the solutions to the nonlinear Sinch-Poisson equation, it's much closer to being perfect correlation. So if you look at this, any equilibrium, either one of these, has the property that the vorticity is a function only of the stream function. So, because then the nonlinear terms vanish in the Navier-Stokes equation. And if you look as a function of time, initially you have uncorrelated vorticity and stream function. And as time goes on, you see that you evolve to this very nice single-valued function, which happens to be, according to this graph, extremely close to the Sinch-Poisson state. So you're evolving more towards the Sinch-Poisson state than towards the selective decay state, but they're actually not all that terribly different. It's just that the most probable state maximum entropy calculation is a little bit more accurate. Now, I reproduced these plots of the vortex gobbling up the smaller vortices to make another point, that these final state vortices are very close to the Sinch-Poisson. But how about these intermediate state vortices? If you look at these intermediate state scatter plots, it almost looks like it's some kind of superposition of many of these final states, but sort of incoherently superposed. And also, if you look in the real space, you see that relatively early on, these towers kind of emerge of vorticity, which look a lot like the final states, but there's a lot of them. So one might think that what's happening is that you are approaching that these McWilliams had postulated isolated vortices, but they're not really isolated, they're still interacting, but they are, a reasonable hypothesis is that they are still locally trying to approach a final state, but defined locally. So it's like a local relaxation process based on what we know happens in the long run. So that's what I just said, that along the way to the final state, maybe what happens in all of these systems is that you relax in local spatial patches to states that look like the final state, and that would be Beltrami, force-free, alphanic, and pressure balanced. That's another reduction of nonlinearity. So the rule, according to a certain interpretation, which is originally due to Kreisman, by the way, is that these local processes occur to suppress the strength of nonlinearities. So the Beltrami suppresses the V cross omega nonlinearity. The force-free suppresses the Lorentz force, J cross B. The alphanic suppresses the V cross B in the induction equation. And the pressure balanced one reduces pressure balances. So it's not an unreasonable hypothesis. And you can ask the question, does it occur? So Sergio Sabadio with Minping, and when all of them were with me 10, 15 years ago, we looked at big Navier-Stokes simulations, and we formulated a way using cellular automata to identify vortices and closed circulation patterns. And here they are colored in. I'm not going to go into the great details, but what we realized is that they're also trying to form locally these single valued function states that look like they're relaxed. Now, which one's relaxed? Green one relaxed, that's this one. That's when this peak of the stream function coincides with the peak of the vorticity, and you get a really nice, clean equilibrium single valued function, and there it is. Other ones are more messy. Those are the ones like the purple ones here. One of the purple ones is highly distorted. It might be merging with another one. And here, the yellow one is really messy, and you see the yellow vortex over here. And the further apart the peaks of the vorticity and peaks of the stream function are, the more messy the scatter plots are, and the more stresses the vortex is feeling. So this is like an ongoing picture of how this local relaxation occurs. Of course, if the vortices keep gobbling each other up, eventually you only have two in periodic geometry, then you're in the ultimate state. So for fun, in this paper, we said, well, Hurricane Katrina had just happened, so we downloaded the meteorological data from the source on the Weather Bureau, and we computed the stream function and the vorticity, and wow, it's actually following mostly a single valued function, except for very low values of vorticity where it's messy, presumably meaning that it's when the hurricane vorticity is too weak, it interacts a lot with things in the surroundings. So I'm not saying that the Hurricane Katrina was two-dimensional, but it's acted in some sense more two-dimensionally than you might otherwise believe. How am I doing for time? Does anybody have any idea?
It's 45 minutes.
We have already,
You can go.
Okay.
You can finish.
So anyway, we talked about suppression, and I told you about these nonlinearities that getting smaller. I'm talking too much, right? So we suppress the nonlinearities, and that gives you the local relaxation. So Anik and I did some simulations in 2008, just looking at the angle between velocity and magnetic field, and we found that in 3D MHD simulations, if you start with no cross-helicity on the right here, and uncorrelated velocity and magnetic field directions, that's the flat line in cosine theta, that within one nonlinear time, you have enhanced probabilities of aligned and anti-aligned velocity and magnetic field. If you have finite cross-helicity, you get a picture that looks kind of similar, except it's heavily biased towards one case. In this case, it's positive, so positive cosine theta. But you can see that the aligned state is increasing in time. So that's one type of local relaxation. Interesting is that Karim Osman took, I think, 56 solar wind intervals, 56, and looked at averaging over all 56, looked at the distribution of cosine thetas between the velocity and magnetic field fluctuations, and that gives this red line. And then, since we could compute what the average cross-helicity was in those 56 intervals, we started a single MHD simulation with that cross-helicity, and then looked at, after a couple of nonlinear times, looked at the distribution of cosine thetas there. And it's not an exact match, but it's probably a lot closer than you might think. And this suggests that maybe in the solar wind, the reason that the velocity and magnetic field fluctuations are directionally aligned is because of a powerful local relaxation process that seems to occur all the time, whether you're velocity shear driven or whether you have magnetic helicity or not, doesn't matter. This one happens in the simulations basically all the time, and it's maybe happening in a similar way in the solar wind. Sergio then came over and was my postdoc in 2008 and looked at all of these correlations, and in fact found that they all are generically evolving towards these kind of suppressed states where you have aphanic, Beltrami, and force-free states according to this minimization principle, but now applied locally rather than globally, saying that in patches you have these correlations. But of course, if different patches are locally relaxing, incompletely relaxing, just like in the hurricanes plots that I showed, along the fringes of the locally relaxing patches, there has to be high stresses because it's not globally relaxed. And that seems to be where all the important dynamics is occurring, like vortex mergers and reconnection and things like that. So there's evidence for these kind of coherent structures. This is the 2D MHD version in pictures. I can skip that. So I think I've already explained the local relaxation, and in this way, the plasma tends to become cellularized with boundaries that are not relaxed. I think that's the important feature there. Okay, so I've talked too long, but the next part I want to talk about, probably the part of this that people are more familiar with, which is small scale structure and intermittency. So I think I can go pretty quickly on this. People know that as the cascade progresses, that sort of each hop that you take in scale tends to increase the non-Gaussianity. So that as you go look at fluctuations at different scales, ones at finer scales have done more hops in Fourier space, and therefore they're more non-Gaussian. So the dissipation range in MHD anyway is highly intermittent in the sense that the increments are non-Gaussian. This is pretty easy to understand. I'm not going to spend a lot of time on this, but if you just say that you have some degrees of freedom, Q and W, if dq dt is QW, and suppose that they're both initially Gaussian, then the right-hand side is the product of two Gaussians. The distribution of a variable that's the product of two Gaussians is more or less exponential. I think it's a Bessel function of 0th order or something. So that means if you put a k in there, because all the nonlinearities have gradients in them, if you had dq dt as kqw, then the higher the k, the more the non-Gaussian pumping is, and therefore you get higher non-Gaussianity as a function of time in higher wave numbers. And of course, you add dissipation at this point, and now you have dissipation occurring in the non-Gaussian structures that are produced by the cascade. So in this view, the fact that there's dissipation enhanced in the coherent structures has nothing to do with why the coherent structures are there in the first place. They were going to form anyway. It's just that it happens to be that viscous dissipation and maybe kinetic Alfvén waves or something are all one of those kinetic plasma things, occurs in finer scale structures. Thank you, Emanuele. Don't make me laugh, please. So all this happens in hydro too. This is one of Pablo Manini's incredibly, well, was at the time, incredibly large simulation of 3D MHD. And you see, without a mean field, the coherent structures, the current sheets, aren't really sheets anymore. They're like baklava, like Egyptian baklava rolled up, or layers of things, very complicated shapes, but they're small scale coherent structures. And again, because it's MHD, the dissipation is localized there. And then here's Antonella Greco's famous picture where you divide up the current into 3 regions compared to a Gaussian, and you see that the region 3 with the strongest tails in the distribution of current, you mask that out and you see sheet-like structures between magnetic islands that are interacting. Here's another picture of the same thing. They have high kurtosis, you know that. This also happens in 3D reduced MHD. This is Franco Rapazzo's simulations showing what happens if you have a very strong mean field in reduced MHD, like in coronal flux tubes. The current can be kind of complicated, but it's here, it's quasi 2D, weakly 3D. So it does form, I'm going to skip Penny's thing. It does form sheet-like structures. And Tulsi Parashar did some simulations, PIC simulations, looking at Orszag-Tang vortex, and there's a central current sheet here. And it's very interesting that the current concentrates in the middle. Just look at the middle. The vorticity forms quadrupoles nearby. The proton temperature is organized in a similar kind of structure. And the proton temperature anisotropy, a little bit more complicated, but it's clear that it's forming structure in that quantity near the current sheet. This is 2D PIC simulation. So now you're starting to see the idea of regional correlation, because you have current in the middle and you have the vorticity is nearby, but not exactly at the current sheet. And the proton temperature anisotropy is again nearby, but spread out a little bit more than even the vorticity is. Notice that the proton temperature is highly correlated to the vorticity, but not so much to the current. People tend to say dissipation occurs in currents. Well, yeah, it does, but it also occurs in vortices. There's a lot more of this kind of stuff. Here's Karamabadi looking at electron temperature anisotropy in shear-driven. And again, there are small-scale coherent structures at electron scales. Energetic electrons with more than 5 V thermal, again, are distributed in a very non-space-filling way. there's a lot of papers on this kind of stuff that has emerged in kinetic plasma showing that dissipation occurs in subsets of real space, fine scale things, usually organized around inertial scales of the plasma. Osman did this paper in 2011 when he was working with me as a postdoc, and he looked at PVI, which is Antonello Greco's way of detecting strong gradients. Think of it as being a surrogate for the current. When you can measure the current, they're correlated with one another. But high PVI regions are more small scale structures. And you see, if you look at the proton temperature distribution conditioned on PVI, the low PVI has this black temperature distribution. As you go to higher and higher PVIs, finer and finer current sheets, the temperature distribution systematically moves to the right with stronger tails. So this indicates that there's more heating, or at least more temperature, in regions that are associated with sharper gradients. And then there's also transport boundaries in solar energetic particles, which are patchy again, and there's not an agreement as to what causes these. Some people say they have to do with sort of patchiness on the surface of the sun, okay? But also if there's flux tubes extending into interplanetary space, it could be that the energetic particles that the flux tubes are acting as conduits, and they have a little bit of a hard time to get out of the conduits. So you see these pipes, basically, of energetic particles. Again, now this is a structure, a pretty large scale structure here. And okay, pick simulations, just to show you that everything is intermittent in the sense of being non-space filling. Current density, electron J dot E, proton J dot E, the spectral transfer at 5 DI, electron pressure strain, proton pressure strain, electron temperature, proton temperature. Every single thing you look at in kinetic physics is organized in some complex way. If you do correlation coefficients among these things in pairs, they're in general not point-wise correlated with one another. They're correlated in patches. You have to coarse grain to see the correlation. And I showed you the reason for that before, because the vortex quadrupole is centered on the current sheet, but it's not at the current sheet. So there's regional correlation of all of these things. Okay, that's the spatial domain. I did large scale stuff. I did small scale stuff. I showed you that. But how about the time domain? Well, interesting fact, and I'm not going to try to document this to you here. As far as we know, all inverse cascade systems exhibit 1/f noise. Very interesting. If you take one of those Gibbs systems, or even one of those pseudo-inverse cascade systems, they do it too, as far as we know. But let's stick with the Gibbs system. If you have two strictly occurring invariants or some quasi-invariants, and you look at a point, and you measure the time domain signal for very long times, we're not looking at spatial structure here, purely time structure, you'll see 1/f noise if the system is a two-invariant system or a quasi-invariant system. You can get quasi-invariance by rotation, by strong mean field, or strong mean field in a penning trap, and all of them exhibit 1/f noise. As far as I know, there's no theorem to prove that occurs. So that means that the systems that generate large-scale structure in space are also generating very long period structures in time, which is kind of interesting. There's no theorems for condensation in frequency, as far as I know. Somebody else has to prove all of that. You can look at a dynamo model to see all of this happening. This is with Dimitrick and Manini and those guys. If you take a spherical dynamo with a few hundred degrees of freedom, perfectly conducting boundary, so it's a Galerkin system, you put no dissipation and run it for like 100,000 nonlinear times. You can do this with no rotation and no helicity. And in that case, you don't see any. This is a 1/f spectrum here. You don't see any 1/f. It goes flat at low frequency. If you add rotation and no helicity, you have a couple of decades of 1/f noise. If you do helicity and no rotation, same thing. You get kind of f to the -5/3 at high frequencies, but you get 1/f at low frequencies. If you have both rotation and helicity, you also get 1/f. So both of these invariants here. The helicity is actually an invariant of this system. The the rotation produces two-dimensionalization, which gives you a quasi-invariant. So both the invariant and the quasi-invariant are at work here, and either one of them seems to be associated with generating structure, low frequency structure in the time domain. And you can also look at the dipole reversals. When you have the one-over-f noise, you tend to get waiting time distributions of the reversals, which are power law, which could be of interest to people. Let me not talk more about that. So I want to come to the end now, I wanted to bring, I brought time domain back into it, and most of the talk was about large-scale structure and small-scale structure. So I want to remind you of something in the classic literature. Oh, I told you I was gonna come back to Grant, Stewart, and Wallier. So it turns out that in Les Calanques in France in 1962, they had a conference in which Grant, Stewart, and Wallier, I think, were all there, and Ubukoff and Kolmogorov were there, and so was Keith Moffett, who I heard speak about it 50 years later in the same room. But apparently, Grant, Stewart, and Wallier got up in front of the audience, and every classical turbulence person you've ever heard of, just about. Batchelor was in this, G.I. Taylor was in the room, Ubukoff, Kolmogorov, Emelianskikov, Novikov, it's just an amazing turbulence conference. And Grant, Stewart, and Wallier got up and they showed the picture that I showed you of the minus 5/3 wave number spectrum. And the next talk after them was Kolmogorov. And Kolmogorov, and this is from, I heard Keith Moffett give a talk on this. Kolmogorov got up and said, well, that's all fine and well, but it's wrong. And he said, the problem is, as Landau has pointed out, the epsilon, the turbulent decay rate is not a constant. And in Kolmogorov 41 and Ubukoff 41, the turbulence decay rate is a constant, but it shouldn't be a constant. Landau said, it's random. It has to be a random variable in your theory, and you have it as a constant. So you have to work on it. It took them a while to do it, but Ubukoff and Kolmogorov solved the problem, as we all know. And Ubukoff led the way, actually, and he said, quote, although each measurement is satisfactory in agreement with the 5/3 power law in a certain range of scales, the intensity of turbulence, that's the epsilon, varies from measurement to measurement and may be explained by variance of the energy dissipation rate. These slow fluctuations of energy dissipation are due to change of the large-scale processes in the observed region or the weather in a general sense. Similar slow macroscopic changes of energy dissipation must be observed at large Reynolds number as they're actually observed in the atmosphere. And when I went back and read this some years ago, I realized Ubukoff's not talking about dissipation range intermittency. He's talking about like burstiness of long wavelength, slow fluctuations that obviously if you have a big, like a storm comes by, it has more energy dissipation than a laminar flow region, but hydro and weather is characterized by that. So interestingly enough, this was from a 62 paper from that conference in Les Calanques. So Kolmogorov said in his paper, which was written after the conference that I was talking about, he said Landau noticed that they, meaning himself and Ubukoff, did not take into account a circumstance which arises directly from the assumptions of the random character of the mechanisms of transfer of energy from the coarser vortices to the finer. You notice that there's no statement that you have to be in the upper inertial range or in the dissipation range. It's any from coarser to finer vortices. It could be 1,000,000 kilometers to 100,000 kilometers. However, Ubukoff has now discovered how to refine our previous results in a way that takes into account Landau's comments. So Kolmogorov then presented this at that conference in 1962, the so-called Kolmogorov refined similarity hypothesis, upon which all multifractal theory and intermittency theory is based, is by saying that this thing has a universal distribution at high Reynolds numbers. Now notice delta U and epsilon are both, epsilon at scale L are random variables, but we don't need to go into the details of that. But the conclusion that I draw from going back and revisiting this is that the fundamental character of energy dissipation is that it fluctuates at both large and small scales. It fluctuates at all scales. what emerges is structure at all scales, at a wide range of spatial and temporal scales that contribute to intermittent energy dissipation. And I would propose the idea, I mean, it's their idea, not mine, that it's Ubikov's intermittency at large scales. The large scale intermittent structures are sort of Ubikov's idea. And the smaller scale intermittent structures are Kolmogorov's from the refined similarity hypothesis. So I think we should maybe start thinking about, maybe you want to not use the word intermittency, but I like intermittency to mean fluctuating energy dissipation in the same sense that Ubikov and Kolmogorov said it here, that turbulence produces structure, and the structure can be at long wavelengths, short wavelengths, long time scales, short time scales, and there's something universal about structure formation, and there's a lot of different ways to study it. And I think that's the end of my talk. Thanks. Come on, Emmanuel, you've got to have a question. He's saving the tough questions for afterwards. He's going to hit me with them. Yeah. Yes. This one.
So at the end, when you said no, it looks like a small difference superimposed the intermediate time, so it's like many different random whatever superimposed. Yeah. So, and at the end you get only one, right? Because you're reaching the size. So it looks like if you will have a bigger system, that
they keep going. Yeah.
So is there a kind of a self-similarity argument that you can apply in scales?
For the intermediate stages.
Yeah.
I probably, sounds like a good problem to work on. I don't think anybody's done that. But yeah, I think you're right. And it's interesting that even in this state, at the end, the vortices are very slowly oscillating and drifting. And it turns out that even the small ripples that are left over are still causing really slow dynamics. Remember that the decay time for these vortices, this is like 374 nonlinear times. The decay time is like 50,000 times. So they're going to do this for a long time. But at this stage, what they see is a periodic potential called an Ewald potential, which looks like a crystal. And in fact, studying the dynamics at this very late stage is almost condensed matter physics, I would say. But it's like a vortex crystal. They form vortex crystals. People have even formed vortex crystals in penning traps. I don't know how to do it, but people have done it. But you're right, at this stage, you can see both the coherent structures and the kind of Kolmogorov-like 2D turbulence in these ripples in between. So I think that, the decay law, I think Rick Salmon at Scripps did something about a power law in time for the number of vortices. That might address the kind of thing that you're talking about. I had one of my grad students look into that a while back, but people don't look at this kind of system very much. It's pretty esoteric. You don't see 2D vortex gases very frequently. The weather, the hurricanes, approximately.
I have some technical questions, but I will skip them. So I have a question concerning your conclusion, because when linking the Opukov and Kolmogorov, isn't that link related to the fact that you don't have any energy source and sinks in the LSR range? I mean, in the sense that if you inject more at large scale, you get more in the distributive scale, at least in the MHD framework. And then a further question, since this lecture has been really, let's say, really broad, in the scope, and it was very nice. So a broad question, in a horizon of like 20 years, what do you think that is the most relevant problem one should look at?
Really putting me on the spot there. I can tell you I can hint at what people are working on. I don't want to give away people's PRL submissions too much. But Giuseppe Auro is looking at, you know him, right?
Yeah.
Big Sicilian guy. He's looking at scale filtering in time and space, and looking at directions of transfer in time. Sort of like something like cascade in time. But it's interesting that in his work, he's finding, hopefully paper will appear very soon, he's finding some limitations due to the injection mechanism. Because if you inject at the scale of the system, then the energy doesn't have any place longer to go, right? But you can still look at the fluxes in frequency and tell something about what it's trying to do. I think there's a lot more to do on these subjects. Unfortunately or unfortunately, these simplified models exist that allow you to actually make progress in understanding what might be the more profound consequences, but actually applying them to like weather or something, or even the solar wind, can only be done kind of indirectly. But I think the corona is a place. If we get good enough data in the corona, maybe you can start seeing some of these things where merger of coronal flux tubes. We need MMS in the corona. Can somebody arrange that? Denise, come on. The Italian Space Agency can send 4, 6, 8 spacecraft to the corona. Why not? You know, you can try. Did I just do lobbying to the government here? I don't know. I'm allowed because I'm an American.
Okay. We know that there is a question on the web. So
Yeah, but I think it will unmute and ask.
Can I ask you my question?
Hello.
B. Again. So first of all, thank you so much for the seminar. I think we all desperately need to the theory every now and then to understand what we do, especially when we analyze observation. Okay, so if I can summarize the first part of your talk, what it says essentially that if you do equilibrium statistical mechanics of the truncated system, it can be either fluid or the plasma. Then if you have more than one quadratic environment, the equilibrium can develop. Let's see one of the two environments piling up at line. And this is what we call.
sorry, can you repeat slowly because we cannot hear very well.
Okay.
Much more near the microphone, please.
Okay.
Sorry, Raffaele.
Let me try again. Can you hear me now?
That's better.
Yeah, that's better.
Okay. I was saying, first of all, I was thanking Bill for the great dip in the theory. So I was saying, I was referring to the first part of the seminar where you tell us about equilibrium statistical mechanics, which applies, of course, both fluid and plasmas. And when you have more than one quadratic invariant, new equilibria can develop that see one of the two invariants piling up at large scale. And this is what we call inverse cascade. Now, the problem that, at least in the fluid community, we have trying to explain essentially the weather, so the formation of large-scale structures in the atmosphere in particular, is that if, in fact, you have the inverse cascade of one of the two quadratic invariants, the same invariant cannot cascade to the small scale, which poses a problem if you want to have a system that has large-scale condensation and turbulence, say, in a smaller scale inertial range. Now, in the solar wind, of course, we can come up with several hypotheses of what are the quantities that are conserved, and in the end, which are those quantities and what is the dimensionality of the system would determine whether we have an inverse cascade and whether this can coexist with what we observe, which is in fact, for instance, if we talk of the solar wind, is in fact the solar wind in a highly turbulent state. And you correctly pointed out that the one thing is to say that there is an inverse cascade, and another thing is to say that there is an inverse transfer, so there's some energy going to the large scale. So my question is, what do you predict for the solar wind? So what are the relevant quadratic invariants that we should try to build an equilibrium statistical mechanics theory upon? And if you would expect that there could be an inverse cascade that coexists with a forward energy cascade. So having both at the same time, which is what the observations seem to suggest, but no one has a definitive answer so far.
Well,
Thank you.
of course, that's a difficult question, Raffaele. And of course, the solar wind is an open system, not closed. So there's going to be some rough edges in the argument one way or the other. I think the corona might be a better place to understand that, because the flux tubes and flux ropes stick around for a much longer time. But I think one also has to remember that the metastable states, the long-term relaxed states, vary in these systems. For example, that Cinch-Poisson state for the 2D Navier-Stokes is going to last for tens of thousands of nonlinear times. What the analog of that is for a highly magnetized plasma, like say the corona, I'm not quite sure. It could be the existence of large magnetic islands, which I guess are observed. How large they are might depend on how strongly it's driven, because the driving is going to drive it away from the ultimate relaxed state. I can tell you what happens in a Penning trap, though, because you can do that in circular geometry with 2D Navier-Stokes. You can also just do the experiment, and that is that because the circulation is a constant, that the metastable state for the Penning trap, even at longer time scales than the strong isolated vortex in the center, there's a much longer lived state, and that is a rigidly rotating disk that still conserves circulation. And there's no reason, really, if there's no losses at the boundary, there's no reason for that to ever dissipate. That's a real equilibrium if you have ideal boundaries. So I think it's a great question. And what we do know is that at the shorter time scales, that it looks like in the solar wind, there is some local relaxation. Sergio has a paper on that in the solar wind, and Francesco Pecora has a paper in the Magnetous sheath, which I didn't show here, showing that these Beltrami, force-free, etc. states actually appear in the sheath. But that doesn't answer your question, because we're not saying what happens at the longest, like boundary-related length scales. We're not addressing that with obviously MMS, which is only 100 kilometers or 10 kilometers apart. So you probably need a constellation of spacecraft. I'm looking at Denise again. Put this on your shopping list. We need a lot of spacecraft in the magnetosphere. I think that means we need plasma observatory. So with that, I think I've given you your most important answer.
Okay, so thank you. We will have a chance to talk about this after the
I'll see you at AGU. By the way, you're going to probably hear my Lorentz lecture, so you'll hear this a second time.
Yeah, probably. Yeah, probably. I will be with you on the podium. And I would like to point out for the audience, since you made this historical reference, that Benoit Mandelbrot was the first Lorentz lecturer awardee.
The first Lorentz lecturer was who?
Benoit Mandelbrot, the guy you mentioned at the beginning of your talk.
Mandelbrot. How do you say it? You said it in French.
I fake French, so don't rely on me.
How did you say it? His name again?
Mandelbrot.
Okay. Merci, monsieur. Thank you very much, Raphael. We'll be seeing you. Thanks for your comments and questions.
Thank you, Bill. Thank you, everyone.